Hi, this is Jasmine Perez and Stephanie Velasco, and today we'll be discussing to you Project 1. We decided to do the NAE Grand Challenge on providing access to clean water. It is important to realize that 1 out of 6 people do not have access to clean water. So, as engineers, we need to find a way to provide access to clean water for those people. We were provided data from an engineering company who designed a water filter, and they provided us the x, y coordinates and x, y velocities as an Excel spreadsheet. So the first thing we need to do is import the Excel spreadsheet onto MATLAB. And as you can see here, we use an XLS Red, and the data name is atomic data. And here are the cells from the Excel, and we inputted it as a number text raw format, so that the number will be the number matrix from the atomic data Excel, and the text would contain all the text cells from the atomic data Excel sheet, and the raw would provide us with the number and the text, so basically everything. Second, we calculated the cross area of the water filter that was provided to us. And we also calculated the density of the water molecule, which is 1 times 10 to the negative 24 kilograms per nanometers cubed. And we use nanometers cubed because the data that was provided unto us is in nanometers. The data is divided into 26 time steps, starting from 8700, and as increments of 500 up to 99,500. And by dividing all of the time steps, we got the x coordinates of all the 300 water molecules, the y coordinates, and the y velocities and the x velocities. And what we did was take the average of the x coordinate positions of all the 300 water molecules and gave it a variable. And we did that for the x velocity also, the y coordinates, and the y velocities. We also calculated the magnitude of the x coordinate average and the y coordinate average for the corresponding time step. And we also calculated the mass flow rate for the corresponding time step using the x average velocity. And we did that for all 26 time steps, as you can see here. And we plotted the position versus time for the x coordinate versus time, the y coordinate versus time, and the x and the y velocities versus time. And so we'll run the program to explain it more to you. And as you can see here, we have the x and the y position over time. And we did this to get an idea of how the water molecules, the average water molecules, are going through the water filter. And we also did the displacement versus time to get a general idea of how the water molecules are moving throughout the water filter. And we also did the y and the x velocities to get a general idea again of how the water molecule is moving throughout the filter. As you can see here, we have the graphs, and we also calculated the polyfits. For the x velocity, we did a polyfit and we got a linear line. However, for the y velocity, we got a sine function. And to get this, we actually used an app on MATLAB called curve fitting. And so you input the x data and the y data for the curve fitting tool, and then you mess around with it, and then you try to get a trend line that fits the most to your data points. And as we can see here, sum of sine is the best fit for our data point for the y velocity versus time. We also graphed the pressure gradient versus time and the flow rate versus time. As you can see here, we have the graphs, and the pressure gradient, which is the change in pressure over the change in distance, is pretty much 0. And we need to realize that the higher the pressure gradient, which means higher the pressure, and that would mean higher velocity, and that would increase the back pressure of the filter, which would mean that more pump power is needed. So it is important to keep the pressure constant, to keep the pressure gradient basically zero. And that would mean that the velocity wouldn't increase, and this would minimize the back pressure, which would allow us to save pump power. And this would also mean that we would reduce the mechanical stress on the filter. And that would also mean minimum cost to create the filter. And this would be efficient for us who are making the filter. It is also important to realize that we need a low flow rate for our water filter, because that would mean that solid particles can clump together and make it easier to filter out the water, because the clump particles will struggle to get through the water filter. However, if we have a higher flow rate, that would mean a higher velocity, and that will break up the clump molecules, so then the filter wouldn't be able to block the unwanted molecules. And so we also need to get a laminar flow. And here are the pressure gradients. As you can see, we use a pressure function that we created to calculate the pressure of the corresponding coordinates. And we calculate it by calculating the density of the water times the G times the depth, which we got from subtracting the y coordinate average from the height of the pipe. And so we calculated that. In our water filter, we need to get a laminar flow. And to calculate that, we created a function called flow. And it is over here. And so basically, it'll multiply the fluid density, which is water, times the fluid velocity of the water, times the diameter of the pipe, over the fluid viscosity of the fluid. And so if the Reynolds number, which has no units, if it's below 2100, that would mean that the flow of the fluid is laminar. And if it's over 4000, it would mean it's turbulent. And for our water filter, we need to get a laminar flow, because a laminar flow would mean that the water molecules aren't going crazy, and it would mean that the velocity isn't as high. So that would mean that we would be able to block out the unwanted molecules and filter out clean water. And so we'll do a test case. We'll do a laminar flow first. So the density of the water is 1 times 10 to the negative 24 kilograms per nanometers cubed. And we need to keep all of the units constant. And for this one, the fluid velocity, we'll use the vector, which we got a while ago, which are the x averages. And we'll just copy and paste it. And then it'll also ask for the diameter of the pipe, which was given in the data, which is 22.2457. And the viscosity of water depends on the temperature, but we'll keep it as 8.9 times 10 to the negative 25 kilograms per nanometers times picosecond. And so when you press enter, we get that the flow of the fluid is laminar. That's what we want to get. Now we'll run it again to get laminar turbulent flow this time. And we don't want to get turbulent flow because we won't be able to filter out the water, the unwanted molecules, and we won't be able to provide access to clean water. So we'll keep everything constant except the velocity. And this time we would input the velocity as 200 nanometers per picosecond. And the diameter of the pipe is the same. And the fluid viscosity will also be 8.9 times 10 to the negative 25. As you can see here, if the velocity is high, we get turbulent flow, which we want to avoid. So for our code, we ran into some limitations. The atomic data that was provided to us are in nanometers and in nanometers per picosecond. So we had to create a code that would return data in nanometers for coordinates or nanometers per picosecond for nanometers cubed. Also, for our pressure function, we inputted the density of waters in kilograms per nanometers cubed, and everything here is in nanometers per picosecond and in nanometers. So our code wouldn't work for data that are in, say, meters for the x and the y coordinates or meters per second. You wouldn't be able to calculate the pressure using this function. And for our code, it is good that we created this because later on in the future, if you want to create a filter, we'll just input everything in nanometers and picosecond, and we would try to get an ideal velocity because we want to achieve that laminar flow to filter out the water molecules and keep everything that we don't want inside the filter so that it wouldn't be in it wouldn't be in mixed with the water molecules. And that's all.